All right, so picking up where we left off, here's another, I think, very important it's small but very important idea about how to program effectively in ML, which is to make errors that may show up in the functions that you call as clear and explicit as possible. At least to make common errors obvious. So this actually connects to another idea that people will often say about programming outside of the context of ML, which is use exceptions for exceptional circumstances. Right? So why do people like to say this? It's because exceptions are, first of all, in some ways a kind of messy control flow structure. It's like, and then I'm going to do this thing which unwinds your stack up until where you catch it and like leaves your logic in a somewhat confusing intermediate state. Right, so that's one of the reasons people want you to minimize the use of it. But the other one is that in many contexts, exceptions are kind of an implicit error handling thing that you kind of, like, what's great about exceptions? Well, they handle errors implicitly and you don't have to think about it. And what's terrible about them? Well, they handle errors implicitly and you don't get to think about it. Right? And no one really enjoys thinking about the error conditions in their code, but also no one is so excited about their code crashing all the time either. And thinking about the semantics of your code in the presence of errors is very important. And you want to write your code in a way that makes that thinking as easy as possible. Right? So I wouldn't go so far as to say one shouldn't use exceptions. I think exceptions are a totally valid and useful programming construct. But you want to be very careful about them. Another interesting point about this idea of making using exceptions only for exceptional circumstances is it's often hard to know at the time that you are writing a library, say, to know when someone is using that library, are the exceptions that you're throwing, do those correspond to exceptional circumstances, or do they not correspond to exceptional circumstances? Because it's often very dependent on the context in which you are using the library. So imagine that you're using a library that has a function for finding an element in a list. You can imagine two different ways of writing that type. In fact, let me actually pull up some code. So here's a kind of snippet of what would be a reasonable interface for a list library. So look at that first function, find. So in fact, there's two functions, find and find_exn. And the idea is the first one reflects the fact that the thing you're looking might not be there, reflects it in the return type. It gives you back an option, which then in the code that handles the result has to explicitly deal with that option. And the second one is more implicit, right? The function always returns the value. There's no data type indication that it might not succeed. But as indicated by the name, it might throw an exception. And if you think about it, the question of whether or not that exception is really an exceptional circumstance is very context dependent. You might be writing a piece of code where you know for sure that the thing you're looking for is somewhere in there, but you just don't know where it is, and so you use the find function to find it. And it might be that you really don't know whether it's there, and there's some real ambiguity, and you want to be explicitly notified when it's there and when it's not. And so our practice is to have multiple versions of the interface of the type signature for the function. One that is explicit in its type, that an error might show up, and the other that is explicit in its name, that an error might show up. Right? So this is what this _exn thing is. So we have kind of fairly uniform naming conventions. And when there's a function that, as a kind of, that easily, depending on its inputs, might throw an exception without it being a clear bug case, we will put _exn in the name. And most of the time, we'll have it explicitly return an option. And in code that's well behaved, the right thing to actually do is to use the one that does not throw exceptions. Because you're usually better off having the type system know about it and not just have the programmer know by the naming convention. This is a thing that we've learned actually by hard example, and in fact, over time have kind of gone back and redone much of our code base in this style in order to increase the robustness of the code. This actually goes back to the thing I was saying before about a lot of your lessons about how to program depend on your point of view. There's an extremely smart guy who works at Jane Street named Stephen Weeks, he's the author of Milton, which is the kind of ML compiler that produces the most efficient ML code basically in the world. And when he came to Gentry, he said that his ideas about how to think about error handling changed a lot when moving from the kind of systems he was writing to moving to the kind of systems that we do. Because if you're writing a compiler and the compiler, dies with an exception and leaves a stack trace, it's not wonderful. It's not the best way of returning an error, but it's not really that bad. Whereas when you're writing a trading system and it suddenly in the middle of the day dies and gives you a stack trace, you're very, very unhappy. And so again, your way of designing software will depend a lot on what you need that software to do. And the other thing that's nice is that if you look at that last function at the bottom, the fold, well, unlike find and head and reduce, fold doesn't require a non-empty list and doesn't require that the element that you're looking for actually be there. And so fold has neither the _exn nor does it return an optional value. And so you can in some sense go and take that fold and use it with an extra level of confidence and not have to think so much about whether or not this thing is going to blow up. Right? So being explicit about your error conditions both makes it easy to think about errors when it's not there and makes code that is simpler because it has simple error behavior also easier to think about. So here's another one. Avoid boilerplate. So there's a lot of boilerplate code in the world. I think people's first instinct when they start learning how to program is, I'm going to do this thing, and then when I want to do something similar, I'm going to copy it over and make a couple of modifications, and then I'm going to copy it over again. And you can sort of see this with people who are starting out programming. It's extremely common. And sometimes it is there for a good reason. Sometimes you have boilerplate because there's no other way around it. And to understand why boilerplate should be avoided, you understand why people do it. Right? The main reason why you have boilerplate, why sometimes even very good programmers use boilerplate, is because there is some pattern that they want to have occur multiple times in their code base, and the pattern is not well expressible within the language they're using. Right? If it was really well expressible, there'd be no need for the boilerplate. You wouldn't have to do the cut and paste. Sorry, there's a question? Yeah?
What is a boilerplate? Is it just
yeah, by boilerplate, yeah, it's like, yeah, I don't know where the phrase comes from. Basically, like when you take a piece of code and copy and paste it all over the place with minor modifications, that's called boilerplate. I mean, it's called boilerplate when it comes up in legal documents too, right? It's not just a feature of code. In fact, I've come to think of lawyers as programmers with really bad tools. Because they also have like definitions and shared pieces of enormous document bases with shared information, and it would be great if they had good version control, but they really don't. Anyway, so in some sense, the core reason why people have boilerplate is because they don't necessarily have the abstraction tools at their disposal, either because their language doesn't support it or because they don't really know how to use them, to really represent this pattern as a reified thing that they can directly use repeatedly in multiple places. So instead, they kind of do the next best thing, which is copy it and make little modifications. And it's worth also understanding that boilerplate is almost never exactly the same thing. Right? It's usually you kind of copy something over as a template and make some modifications. And the modifications are actually quite important. Right? And in fact, it is the fact that these little modifications which often prevents you from doing it through some nice abstract facility in your language. So why is boilerplate a bad idea? There are two basic reasons. One is these patterns that you have repeated in your code base are part of the system and will evolve also. You will at some point need to change that pattern. And probably you're not going to do a good job of remembering all the places where you use the pattern and modifying it appropriately. Whereas if instead of repeating it over and over, you had it focused in one place in the code, you'd have a much better chance of finding that one place and changing that one place and having the effects filter everywhere. The other reason it's important to avoid boilerplate is dull. And it turns out human beings are unable to actually carefully read things that are very dull. Like, you cannot pay people enough. I've tried. Like, you cannot pay people enough to actually carefully vet really, really dull code. Like, there's the same thing almost in multiple places. They'll look at the first one really carefully, and the next one will be like, yeah, that's about the same. Oh, and the place where the sign is supposed to be shifted, yeah, that's about right. And like, their error rate will go way higher. So if you care about people really being able to read the code, boilerplate is a real problem. And in C, if you're a C programmer, there's a good excuse for using boilerplate. because C does not have very good, C is great for a lot of things, but it does not have good abstraction capabilities. So if you want to avoid boilerplate, in C you basically have two choices. You can use the macro system, which is there but has its own downsides, or you can copy and paste code. But in ML, there is no excuse. You have functors, you have higher order functions, you have great abstraction facilities, and you should use them. And it is worthwhile to kind of, as a default pose, reduce your tolerance for boilerplate to 0. 2 times is too many. And even to the point where sometimes getting rid of boilerplate may make your code longer, but it's still a good idea. Right? It might be that the shortest thing to do is just kind of repeat the same pattern 3 times rather than creating a local function that abstracts it out once and calling the local function 3 times. But the reason it's better to do the latter is because the latter is more explicit about what is constant and what varies in the pattern. Right? So it often will increase the readability of your code because you state the pattern once clearly, explicitly, with what, and the arguments to that function are the holes in the pattern, and then in the place where you're doing the repetition, you're explicitly just kind of pointing out to the parts that vary. And it makes the overall code kind of more coherent and easier to follow. So here's another one. So this is not yet a problem that you have, but ML is a really fun language. Haskell is a really fun. There's lots of these cool languages in this family, and they're really fun to play with. And they have these cool type systems. And they're really powerful. Like this thing I was saying before about algebraic data types having a lot of expressive power, like that's true. And there's also other parts of the system that have this kind of nice combinatorial flavor which allows you to build really complicated stuff. And it's fun because you can embed all sorts of invariants in the type system. But at some point, you get stuff that's just too complicated, right? I've certainly had the case where like some guy, got enthusiastic and came up with some idea about how to enforce some clever invariants, and came up with something that, like, a highly experienced ML programmer who's been doing it for years and years looks at the interface and is like, I have no idea what this does. And like after 15 minutes of explanation, still has no idea what it does. Right? And when you get to that point, you have failed, right? Because as a programmer, as a software engineer, your enemy is not lack of static checking. Like your enemy is complexity. Right? The art of software and technology in many ways is that of mastering complexity. And if by trying to embed all these static guarantees and shove them in wherever you can, you make the system net more complex, you are not helping anyone. Right? So it's one of these things where I think there's a lot of fun stuff to do, and understanding some of these clever tricks is worth understanding, right? Because it's both intellectually interesting and there are places where it can be used. But it's one of these things where, especially as you get more experienced, you need to restrain yourself a little bit, right? Like sometimes you sort of think, I'm having too much fun now. I need to hold back and do something that another human being is actually going to understand. It's tempting to kind of look at this lovely abstract system and think, to kind of start trying to write code for the lambda calculus in the sky, right? You're sort of going to find this wonderful abstract world and write things that work really well with that, and don't actually work well in the human minds of the people you're working with. And again, it goes back to this idea of respecting people's cognitive limitations. And in a similar vein, purity, side effects. So I didn't actually talk a lot about side effects, but so again, this is another one of these twofers, right? There are 2 lessons here. First of all, you should, where you can, write code that does not involve side effects. Right? And I actually don't think, at this point, this is a less controversial idea than it used to be. As I said, like, Joshua Bloch, who's the chief Java architect at Google, has a book which says the same thing for Java, right? Avoid mutability. Why? Because mutability is hard to think about. People think, what is mutation? Mutation, people think, oh, it's the idea that I can change a variable. It's, it's some kind of dynamism, and dynamism is important, so I want to have that in my programs. But mutability is really about communication in a way that I think people don't normally think about. If you think about, like, what's a ref cell? Did you guys do mutability in OCaml yet? Yeah. Right. So what's a ref cell? You can think of a ref cell as a kind of communication channel between different parts of your program. Different parts of your program that share a ref cell can talk to each other by, like, writing things into that ref cell and reading them back. Right. And if you think about it, when you try and understand a piece of code, you want the code to be as self-contained as it can be in order to make it easy to understand. You don't want lots of long link communication channels kind of embedded in the system, because that makes everything more tied together, harder to reason about, harder to understand. And this is why you should avoid mutation. But you should not make a religion of it. There's nothing, mutation is a natural part of programming. Indeed, you cannot do anything of any use without side effects. Right? There's people talk in some ways about the notion of having, Haskell is an example of something that's known as a pure functional programming language. But it's not really a pure functional programming language, because if it was, it would be useless. Right? Because every time you read from a network socket, or write to a file, or look at the clock, or do anything that touches the outside world in any meaningful way, it is a side effect. Right? Haskell is a language that is disciplined about separating out the side-effecting side of your program and the pure side of your program. So all useful programming involves side effects. And again, as you try, people often try too hard to kind of push the side effects as far out as they can from the program, to have it infect as little of the program as they can. And while it's useful to have this kind of separation, you don't want to go crazy. Because it's often the case that you will end up with something more complicated than if you did something in a straight-ahead imperative style. Sometimes, I think most people who care about software don't think of this as a controversial claim, but sometimes the imperative version of an algorithm is the easier one to understand, not the harder one. Sometimes when you try and do something without side effects, you have to go to real extremes to get decent performance out of it. And if you had to go to real extremes and generate a lot of complexity, it's not clear that you have net made the world a simpler place. Right? And again, as a software engineer, you should be thinking about the idea of making things as simple as you can make them. So I think that. So I have some other things that I wanted to talk about, but I think actually we're not going to have time for it. So I think I will leave it there and ask if there are any questions.
So you just talked about how all these guidelines for actually writing code to make sure it's going to end up working. But what actually is the review process you guys use before you actually put something out in the wild?
So the first thing is we roughly segment. We have a certain subset of our code base which we think of as the critical path, which is roughly the kind of code that goes between the time you make a decision to do a transaction all the way to it getting to the markets. And we have a kind of fairly formal code review process where there are multiple people, usually always at least 2, usually 3 people, assigned to read every piece of code. And whenever there are changes, there are people who will review those changes before they go into production. And we actually wrote our own system for keeping track of this review and making sure that all the things that need to be read have been read. And by the way, I said we do a lot of code review. We also do testing. There are unit tests and other kind of tests that we do on the systems, regression tests of various kinds. But I think code review is kind of the core thing that we do to keep our systems safe and coherent.
Do you have any suggestions for a book or some other resource for how to organize lots of coders working together in the same project?
Sadly, I don't. I actually don't know. I mean, it's just not. It's a thing we've figured out by trial and error, but not something that I've read much that I've really liked on.
There's one classic book called The Mythical Man Month that everybody ought to read once.
Right. Although in some ways it's about a very different world.
I know, but there's one lesson to take away, which is throwing more people at projects typically reduces productivity.
Right.
So.
Yeah. So one thing that this is I think I've certainly read the book that Greg suggests, and that's a lesson that we've taken away from that as well. In fact, one of the things that we've tried very hard to do is try and organize our software development so that people are working on coherent projects in small groups. I think the number of people working on the project varies from 1 to 6, kind of at the outside. We try and keep things keep small orthogonal pieces that individuals can keep in their heads. And that makes it much easier to get big things done, to have sort of people working on lots of small things that fit together well in one coherent world, rather than people I wouldn't know how to manage a project with large numbers of people kind of directly working on the same piece of infrastructure. And we try to avoid that kind of system.
So if you do this kind of high volume trading and market making, which decisions are made by people and which decisions are deferred to software?
So it is enormously variable. There are some businesses that we have which involve like people making phone calls and talking with other people and negotiating trades, and some businesses that we have that involve automated systems that run for hours at a time without humans doing more than kind of watching and paying attention but not really making changes. And there are systems all the way in between. And so it's a very diverse business. I think there's only a fairly small set of things that are kind of low touch. Most of the systems involve significant human interaction. I think someone who hears me talk about Jane Street from the technology point of view will often get the mistaken impression that the business works like this. Like you walk in the morning, like you go turn on the servers, and then you walk to your desk and think big thoughts and write programs and come up with models. And then at the end of the day, you walk out and you pick up the bucket of money and you go home. And this is not how it works at all. It is a very active, intense place. There are lots of people who are paying close attention to the markets, both on the technology side and on the trading side. And that kind of human attention is actually very important to the kind of work that we do. I think because trading is fundamentally a game-playing, a kind of game-playing system, right? Every time you do a trade, one of the key things that people often get wrong when they think about trading is they don't model the fact that there's somebody else. Right? It's like, I think I know what's going to happen, so I'm going to make a trade based on that. And I don't think when they buy those shares of Cisco because they think it's going to go up because this internet thing is going to be big, there's someone on the other side who's willing to sell it to them. And like, why do they think you're smarter than the other guy? In poker, the fish is the guy who's funding the game, knowingly or unknowingly, and by kind of leaking expectancy into the game. And there's a saying that if you look around the room and you don't know who the fish is, you're the fish. Right? And I think that's one of in trading, this kind of human element is very, very important. And it's a kind of central piece. And so these systems that we have are kind of highly integrated kind of human technological systems.
Has Jane Street always used a camel? And if not, then what's behind the decision to use a camel?
We have at this point used it for a long time. So it's been, as I said, it's been about 9 years now that we've been using OCaml. Before we used OCaml, we wrote code in, well, actually, our original systems were VBA running inside of Excel spreadsheets. And we moved on from that to using Java and C#. At the time where we chose OCaml, so there's a whole question of why OCaml versus Java and C#. And in some sense, this talk is about that. And your whole experience here in the class will tell you more about that. The question of why we didn't use Haskell or SML or various other languages is, I think, first of all, I think at the time, OCaml had the most appropriate implementation for the kind of work that we do. It was a little bit random, like I happened to know OCaml, and I was the one who kind of started this whole crazy functional programming thing, so in some sense it's just my fault and probably a mistake. But there's the question of why not Haskell. There's actually a sort of strong reason not to use Haskell, which is it's much, much, much harder to reason about the performance of Haskell, specifically the space performance. And ML sits in a kind of sweet spot in language design in that the code that you write is fairly simple and declarative in style, but there's also a straight-ahead compilation strategy that's pretty efficient. And this is just not true of Haskell. Like, the compilation strategy is not straight ahead. Like, much sweat and tears is poured into making it as efficient as it is. And that adds extra complexity to your world. That said, Haskell, I think, is much closer than it used to be to being usable in this kind of environment. But I think when we started 9 years ago, it wasn't close. All right.
Thanks again, Ron.
Thank you.